Good morning, good afternoon, good evening to all of our Geek Speak attendees. We thank you again for joining us this week on another fun-filled hour of SI detail with some of the experts here from Samtec. I'm Matt Burns, Technical Marketing Manager here at Samtec. Joining me as always as my co-host, not co-presenter this week, is Scott McMurrow. Scott, how are you doing today?
I'm doing great, Matt. It's a holiday weekend, and I'm ready to get out of here.
I am too, and Brandon is the last thing preventing me from having a few days off. So we'll look forward to how he does and enjoy the rest of the weekend after that. Brandon is a repeat Geek Speak presenter for us, Scott. But can you give us a little bit background on Brandon and also what he's going to be talking about today?
Yeah, Brandon Gore is a PhD in electromagnetics out of the University of South Carolina, and he's an expert in an awful lot of things. He worked at Intel for many years and has been with us at Samtec for the last few years. And today he's going to give an introductory discussion, presentation on channel operating margin and its use in signal integrity and channel design. So I'm just going to turn it right over to Brandon.
Wonderful. Well, thank you, Matt, and thank you, Scott, for having me back here to talk about something that I've been around the development for, almost a decade now, and that's the IEEE 802.3 standard, which covers Ethernet, their channel compliance metric, which is called channel operating margin. And before I get too far, I just to say thank you to some contributors to this presentation, specifically Stefan Sirku, who gave a talk a couple weeks ago on de-embedding, and then also Rich Mellitz. And Rich is one of the initial developers of this methodology, still heavy contributor to IEEE, and we affectionately call him the godfather of COM. So thanks to those gentlemen for helping here. I wanted to set.
Hey, Brandon, sorry, just one sorry to interrupt. Just one reminder for everybody who wants to enter questions, question and answers. Please use the Q&A feature. Scott and I will be monitoring those, and we will interject at the appropriate time as we go throughout the presentation. Sorry about that, Brandon. Back to you.
Well, that's all right, and please do take advantage of the open discussion forum here. We're here to help and answer questions. But I wanted to set the mindset a little bit on what we're talking about, and that is these electrical specifications when you're looking at Ethernet or OIF or some of the other high-speed digital design guides. And, a lot of times these specifications are maybe they're a little overly constrictive, and that's for a reason. It's because at the end of the day, you want to plug two things together and have them operate. And so to get that guaranteed operation, sometimes the specifications are conflicting with each other. The other piece here is that, if you do better in one specification, does that mean that you get a little bit more room on the other specification? And that's not always clear. And a specific example would be, if I do very well in my return loss mask, does that mean I get excursions in the insertion loss mask or things like that? And really, this is a classic SI answer, but that depends, right? So that's what we want to talk about today. There's a big shift in the IEEE at 25 gigabit per second. So I want to explain what kind of brought that about. Channel operating margin is that metric, and I'll talk about sort of the what and the why, the how and the mechanics of it operating, a little bit beyond the scope of what I've prepared here. But if that's of interest to the audience, then we'll definitely take suggestions and can do a follow-on topic. And then, at the end of the day, what benefits is this to you in your channel design, maybe beyond the standard compliance? And then lastly, there's a behavioral model of the package, and I'd like to explain there and how that's developed. So here's an example of frequency domain mask. This happens to be taken from a 10 gigabit per second specification, and it happens in other data rates as well. But it's pretty common that the different aspects of the S parameters are constrained. I'm showing that with a red line here. And you know, anywhere from the reflections being constrained in a different manner, like ILD or return loss, insertion loss itself. Sometimes we fit that insertion loss to a curve. But in general, some dilemmas that this brings up is, you know, how can I tell if I've done well or I have margin to a mask? And how do I really trade off the differences? The specification at this time frame that came the closest to a trade-off would be the insertion loss to crosstalk ratio. But in general, it's hard to trade off these different masks, and particularly what happens if maybe this return loss comes over the line? Is that a hard failure? And so in general, you get budgeting dilemmas with these type of specifications. The other background is in these standards meetings, you have generally two camps. You have the folks designing the transmitters and receivers, or the silicon. And then you have the folks that are designing the channel and components, the interconnect piece in between the transmitter and receiver, and they have their own perspectives. They maybe tend to see things as their piece is the most important. And so how do you come up with a method that gets both parties talking together and discussing the same, talking the same language and coming to agreement? So the paradigm shift that answers this call is called channel operating margin, but the basis behind it is that, you know, buffers operate in the time domain, not in the frequency domain. And if you have a single bit response, which I'm showing here, sometimes called a pulse response, then you can determine a figure of merit. But to do that, you need the context. And what I mean by context here is that you need to know the minimum requirements that a transmitter is expecting to operate, and maybe more importantly, the minimum reference architecture that the receiver should emulate. And that way you can determine what parts of the signal are compensable versus not, and what kind of filtering and noise can you expect. So it starts with a single bit response.
Yeah, can you can you just explain a little bit more about what a single bit response is?
Yeah, very good question. So, you know, also called the pulse response, but it's the if you hit the channel, if you stimulate it with a single pulse with a width, the UI or the frequency you're interested in, and then you see that pulse come out the other side, is what we mean by single bit response. And so this black curve here would be maybe the transmitter waveform here. Actually, I think I'm expecting to be a received waveform here with some ISI on the tail part, and then the red would be maybe after the equalizer has processed it and removed and corrected some of those features.
Thank you.
Okay, so channel operating margin, a couple things to take away or as you know, key points about what it is. It's a time domain open source simulation. And the output of that simulation is a single metric, and single metrics are very useful when you have a lot of design parameters and you're going through the process of looking at a bunch of iterations, and that's hard to do contrasting with frequency domain mask. It's a closed budget, meaning the inputs to the simulation are the minimum requirements for the transmitter and receiver, and that ties together the loss and crosstalk and other things, and you get to separate out the types, the reflections that might be accounted for by the received architecture. And to me, the most important part is the reference signaling architecture, because it forces the members of the committee developing these metrics to agree on a signaling architecture that it should perform like. And so it gives everybody a good talking point to adjust and debate. And then you don't only get the channel operating margin when you go through these calculations that are described in the standard. You get some secondary results, bathtub curves. You get even the calculations put out some of the metrics on the frequency domain S parameters like the ICN. But there's several secondary results that really help you budget within your channel as you design.
I just want to emphasize the minimum reference signaling architecture. That when we develop a standard like this in the industry for a particular data communication scheme, that we specify the minimum architecture. Actual devices can be better than that, but not worse. So it develops a bounds for which we can use to do simulations and modeling with COM.
That's right, and I would say oftentimes the signaling architecture, probably targets something a little better, just to take into account manufacturing variations and other things that happen. So you're right, it's not a specification for designing a receiver or designing a transmitter. It's minimum capability that's described.
One more question. What is ICN?
ICN, integrated crosstalk noise, and I apologize for putting an acronym out there without, I believe maybe we had a topic on that so far. I might be misremembering though, but in general, you take the crosstalk curve, you weight it with a power function, and you integrate it, and you get a single number representing the crosstalk in the millivolt RMS.
Yeah, that's right. Steve Kruzwick gave a presentation on using ICN and a metric like that for connector evaluation.
That's right. Okay, so here's an illustration, and I'm calling it COM simplified because there are a lot of details here that are described in the standard, and the standard goes through all the math on how you might write a program to perform, and it even provides you with an example code to compute these different steps. But just to give you a higher level view of some of the steps that happen, and it starts with giving the program a S parameter, a collection of S parameters representing the through channel and the crosstalk channels. And filters are applied to those S parameters, and they're changed into single bit responses and get their transfer functions out. And then from those transfer functions and the filters applied, the non-compensable ISI and the crosstalk are converted into voltage probability density functions. Sort of the next step is to take the through response that has the filters applied and get the jitter PDFs like the DDJ. And you also get PDFs of transmitter and receiver noises that are specified. And those are all brought together in a cumulative distribution function from all those at the particular bit error rate. And COM is essentially a signal to noise ratio from all those noise sources with the available signal and represented in dB.
Talk a little bit more about what a PDF is.
Well, yeah, so PDF is a probability density function. So acknowledging the fact that we are in the stochastic domain, here.
All right, thank you. What's the min data rate over which COM could be utilized?
Well, the min data rate. It's a very good question. I have been involved in some 10 gigabit and 5 gigabit COM development. I haven't used it below that. The using COM requires a lot of understanding of packages and jitters and transmitters. Some of the specifications at lower data rates don't maybe give you all the information you need to back out those. But I don't know if I know the minimum value.
All right, thank you.
Mm-hmm. So another way to visualize and illustrate COM, that signal-noise ratio, is something using eye diagrams. And this is just to give an intuition about what COM is representing to you. And so I have illustrated here two eye diagrams that have the same eye heights at the bit error rate, representing in this green dash curve here, so channel 1 and channel 2. The black curve is representing the available signal, and what that available signal would look like on equalized pulse response would be this level here, or the difference in these levels. And so you can see from this illustration that channel 1 has the greater available signal. And then if you take the difference between the BERI height and the available signal, that gives you a noise metric. And so taking the that available signal over the noise gives you your noise signal to noise ratio. And what COM is really trying to answer in comparing two channels is the amount of noise immunity, power noise immunity that channel would have.
Here's a good question just in general about COM. Does the signal value metrics like COM replace any frequency dependent channel insertion loss, return loss, or crosstalk masks? And does it mean that these other parameters can be ignored?
Well, it's different for different standards. I would say that there are scenarios where the COM calculation may be an informative metric. An informative means it's a recommended, but maybe something else like an eye height or frequency domain would be the required part. Or the other way around, where the frequency domains are more recommended, but the COM metric is the normative or the required one. And it depends on the scenario. I would say that the trend has been to replace those frequency domain masks because it's hard to get, I hate to say correlation, but some information, guaranteed information about how something will work from the frequency domain mask. And you know, the overall trend would be replacing the frequency domain mask and maybe having a single loss number as a target, but not necessarily an entire curve.
Right, and one of the things I would point out about frequency domain masks is that they are an attempt to categorize a limit at the worst case, where when everything's at the worst case, if you don't exceed these limits, then it will work. Now, we can debate whether that's really true. And that's why COM came in is, well, what happens when we're not at the extreme limits? All we really care about is what does the receiver see. And so COM then allows us to look at a system where maybe we're not at the max interconnect length. Therefore, we have higher amplitude at the receiver. Therefore, possibly we'll actually have better performance, even if our insertion loss and our return loss isn't as good as a particular mask in a particular um, standard. So I think that's the important thing about COM is it can be utilized not as a worst case overall limit, although that's what it is, but also as a figure of merit for when we're not at the worst case and we can now play with different components. And to me, that's the beauty, is that we can design systems with interconnect that isn't perfect, that doesn't meet all of the masks in the frequency domain, yet we all know it still works when it goes to the receiver.
And I can add two things to that. One is how are frequency domain metrics determined? And again, we're talking channel level, not component level. But for a channel level, what would happen is you would get people that would submit channels, S parameter channels, and then vendors, silicon vendors, would take those channels and they would put them into their proprietary simulator and architecture. And then there would be some consensus around, okay, this channel's too hard, this one's too easy. But everybody was using their own proprietary. There was no agreement on the capability. So that's been a helpful piece, is that you agree and horse trade around that minimum capability. The other thing that's important is the specifications actually tied to receiver compliance. And so the way that a receiver is rated as, let's say 100 gigabit base KR, is there's a test where it has to have a certain amount of loss, a certain amount of noise, and that noise that's required actually goes through the COM calculation. And so it attempts to tie transmitter, receiver, and channel all together in terms of a capability.
Thank you, Brandon. One more question. And so you talk about power noise immunity here, but you're talking about power in the signal versus power noise at the device level that is caused by the power distribution system. Is that correct?
That's correct. I'm talking about that receiver compliance I was mentioning. There are Gaussian noise sources that are added, coupled into those receiver compliance tests, and that's the power I was speaking, separate than the power integrity. Yeah.
Right, and I think you talk about receiver and transmitter noise in the specification further on. So, thank you.
Okay, so. Okay, how would COM be useful to you? And obviously the first one is if you're trying to get a channel that passes a particular standard, and that's a reason to go and either write your own code that in the steps the standard specifies, or maybe download the publicly available MATLAB code. That's one reason. But the other way that it's useful beyond just standard compliance is, if you want to take and understand how much ISI and crosstalk are contributing versus maybe the jitter that's specified or the transmitter and receiver noise here. And so, you can start to do A/B comparisons with channels and see, well, and maybe in this scenario, my crosstalk's dominating, and that's the one I need to go fix in my particular channel. Another scenario is selecting components. Maybe lengths and other things that you're constrained, but you have separate components, connectors to pick from. Maybe you have a particular pinout you're trying to decide on. So, in the context of what the minimum receiver and transmitter can do, you can start to see what is sufficient for your system. Same goes for picking a cable that you may want, or maybe picking the PCB material. And so again, this design decisions, or maybe your connector, your material, and you just want to know where does it stop working. So another way to increase length and determine where you start to be non-compliant. So I'll show an example here of something at 25 gigabit per second. And this was a real scenario that I was doing some time ago, but a lot of us start with a component level only. So I'm showing 3 different connectors here. And I got, I'm plotting the power sum crosstalk for the 3 different connectors. And if we look there, we say, oh, well, there's a lot more noise power crosstalk here in connector A. Connector B is clearly low noise. Connector C has something going on, some type of resonance there. But just looking at that, I might be tempted to say, well, connector A doesn't look that appealing to me. Then I look at the insertion loss, and I say, well, B and C are pretty close. Connector A has some type of impedance mismatch problem. So again, if I'm looking at only component, I might be tempted to throw connector A out. But what COM allows me to do is it's a fast open source simulation with a single metric. So I can take all the variables in my system, the impedance variation, the stub length, the routing length, all the things that I can vary in simulation. And I can data mine now what happens if I substitute in connector A, connector B, and connector C. And on that high volume scenario, I see that, well, connector A didn't quite fall out as the worst performing, again, for this application and for this transmitter and receiver capability. And maybe if I squint, connector A is a little bit better, but it really, if I were just dealing with masks, it's very hard to know if I'm getting the sufficient choice. And so it's very helpful in a large data set to data mine and determine where your solution space is.
In this kind of an analysis, what kind of topologies were you varying in this analysis?
It's been a while, but I believe this was a 2 connector system, similar to a back plane. And I believe I had several different routing layers on the same board. So you get a lot of variables on length and impedance variation in a high volume scenario. And so you set up, it's kind of, you get to play with big data sets now and run through your simulator.
Right, that's the value of COM, is that it executes very fast, and so you can run thousands of simulations to do statistical analysis. If you could just go back to the previous slide that shows the insertion loss and crosstalk. So all of these, if we had looked at if we'd had a mask for power sum of crosstalk, clearly, connector B probably would have met our power sum mask, and connector B would have met our insertion loss, probably have met our insertion loss mask. Yet, when we go to your COM analysis on the next slide, well, there are certain system configurations that even for connector B don't work very well. And the other thing that's really interesting, and if you just look at this in as what my eye would determine to be the highest density regions, there's an awful lot of cases where connector A works. And connector A was the really bad one, right?
That's right.
Yeah, so COM allows us to screen out or screen in a connector or a piece of interconnect that may actually work in your system, even though it wasn't necessarily designed for that standard. This is a really good question here. Is it possible to determine the crosstalk contribution coming from various components in a channel, say the package, the PCB breakout, connector breakout, by using COM analysis?
You can, and that doesn't come out from maybe the, if you were to download the MATLAB code that is an example of COM from the IEEE, it doesn't come out, but by selectively turning off and turning on pieces of your interconnect that you may, assuming that you stitched together different pieces, then you could see what happens if, say, I take a component out, substitute with maybe a, turn the crosstalk off on a particular component, or however. And so it's sort of indirect, you would get that type of analysis.
So one person asked that they were surprised that the COM was so good for such a lousy connector. And so what I wanted to point out here is that COM includes the equalization. Mm-hmm. And so sometimes these bad connectors, even though there's lots of reflections, those reflections can be equalized out and clean up the channel significantly.
That's right. So it's in context of the receiver. If you don't know what your capability or your transmitter receiver, you have to pick the best connector performance by itself, because, well, better is always better, and that saves me headaches down the road. But if I know exactly what can be removed, then again, I get that maybe sufficient choice rather than staying with the optimal choice. The other thing I don't know if I made clear, the COM threshold here is 3 dB, and the reason that it's 3 dB is that why is it not 0? It's because the 3 dB encompasses all the receiver budget from the specification. So I don't think I mentioned that one before.
Right. What are the black points down at the bottom?
They're black because they're outside of this box plot. That's all. So they're the.
Oh, okay.
Yeah, that's all. They're just outside the statistical box plot.
Is the COM 3 dB budget subject to change at higher data rates in the future?
I've seen it go down to 2.5, maybe 2 in some scenarios. Again, it's all the standard participants agreeing that that's what it needs to be. And I would say 3 is the most likely target. There are some scenarios where it's 4. So it really depends on the particular standard specification.
Right. Ultimately, it depends on the receiver architecture and how sensitive, how noise tolerant, mm-hmm. and what kind of equalization is used inside of the receiver. And sometimes it's changed, well, because no topology worked at 3. Mm-hmm. That was reasonable.
That's right.
And I think we have to understand that our silicon vendors often do not want to reveal what they are doing inside of their devices. That's all considered to be confidential intellectual property. And so that 3 dB limit essentially gives them latitude to do an awful lot of things inside of their device and still meet the standard.
That's right.
There's a number of questions that can be categorized as pretty much the same way. We have analysis of connector A, B, and C. Which one meets the standard?
A very good question. Yeah. Well, part of the what happens for Ethernet and OIF specifically, and this is different for something like PCI Express, is the component itself, the connector itself, is not specified electrically. So I have no way to know what that capability is. Now, there's some indirect ways for external cable applications, but in general, a component by itself, especially backplane or mezzanine style connectors, don't have a specification. So it's really, you put it in with everything else in the channel, and that's where you get to specify. And I've got a picture of that coming up, actually.
Can you roll back to the slide that had the bar plot of the noise breakout? Because I think that's important. Can you talk a little bit about this? Because you have ISI, crosstalk, jitter, TX, and RX noise. Because I think this helps in terms of determining where the worst, where the problems are coming from in your system.
Well, the ISI and crosstalk are the two pieces that come from the channel model that you've put in to the simulator. The TX jitter, both DJ and RJ, as well as the noise sources are all part of the specification. So these you don't get to change. And so there could be scenarios where your ISI is low, your crosstalk's low, and you don't work, and it's probably because of these pieces that are set aside as the minimum capability you don't get to change here. And these are just relative examples here, not intended to be actual numbers or anything, but.
Right. I think it's important, when we looked forward at that other picture with all the different connectors, that, connector A, I believe, had really high crosstalk. I don't know what the ISI might have been on some of those simulations, but this allows you to better understand why something is passing. Although you might have high crosstalk, it might not be the limiting factor in the system performance. And apparently it wasn't in quite a lot of the topologies there.
That's right. I mean, I don't recall exactly where these clusters would be if I sorted them out by loss. But it could be this cluster was well below the loss target for this particular standard. And so if I'm running half the loss, I have a lot more signal to deal with more noise.
And again, the scatter plot is just a visual aid. You really have to go into that data and further look at what the different lengths were and what the sensitivity is to different parameters in the interconnect. So again, a lot of questions about how do you take this kind of data, and this wasn't created specifically with COM, was it? This is a composite of a whole bunch of COM data.
Each dot represents a COM simulation at 25 gigabit KR, which is backplane, and I did 7,000 simulations with a bunch of different variables. So it was created.
That looks like a jump DOE plot.
That's exactly what. Well, more than DOE, but yeah, I was trying to do Monte Carlo, but yeah, I was doing a lot of different variables and a lot of data mining, but in general, just to show you what COM allows you to do.
And how long does a COM simulation take?
Well, it's as the data rate increases and the equalization gets more complex, it can be several minutes. I believe back when this was created, it was less than a minute. But it depends on how many equalization loops it has to go through to come to the correct equalization.
All right, thank you.
Okay, so the last section here is to talk about the package model. So I've been talking a lot about a channel, and the way that the IEEE and OIF define a channel is between two test points. And so I'm illustrating there is TP0, TP5, and part of the transmit function I've drawn in this box includes the package. So you have this cut point between channel S parameter and transmit function. Same thing happens on the receiver. And so the standard represents that as a synthetic mathematical model, so I'll get into that. But in general, what I'm hoping to lead you to is that representing this piece of the channel as part of the transmit or receive function gets more complex as the data rate goes up. So here's an illustration of a package where I have a die on top of a package on top of a board. And the silicon piece, the die termination and the parasitic capacitance that are in the die are represented by resistor and capacitor. The transmission line that leads out to the ball is represented separately. There's both a long and a short version of those packages. The thought is to comprehend both big and small chips or different links within the same chip package. And then it's called the ball, but I think it maybe represents a little bit more than the ball, but that's all considered a capacitance of this portion in the board. And that's drawn in purple here. And I wanted to stress that, well, two things. One, these values of all these parameters, and I'll go over some of the exact numbers here, but they're all agreed upon is reference capability by all the participants. And so again, it's more knobs to turn to get agreement of minimum capability. And then the C die that we'll talk about may not be the real value. It may be some effective value from compensation and other things. But that's an overview of how the package is represented. And what's really interesting, innovative during this standard development back for 25 gigabit Ethernet was how this this transmission line model was represented. So that's what I wanted to cover next. The synthetic model is a causal by design closed form solution transmission line. And the general process was someone submitted a 1 millimeter length of package that was solved, I believe, in some 3D electromagnetic simulator. So now you have an S parameter, and then this model was formed around that. And there are several parameters here that you get to control that fitting of the model, but ultimately you solve for a reflection coefficient to get to your return loss and insertion loss of the package. And another important piece is it's extensible by link. So now I get a closed form way to represent a transmission line that's causal, and I can play with the length as required to get a short and a long or in between packages. So I'm highlighting some parameters here. You know, the equations are there in the standard to plot out the insertion loss and return loss, but just to show you how that line is built, because I think a lot of us may think of transmission line modeling with frequency dependent RLGC or some other source. This is a bit different closed form transmission line model.
And I think one thing to point out is all of this modeling of the package, the die, the package trace, the package balls, well, except for the die, which we may or may not have access to, this can all be replaced. You can disable this and include it in your own modeling if you happen to have access to the packaging information from your vendor or whatnot. That's correct, right?
You can. The configuration sheet that drives the MATLAB simulation, or maybe your own code, you can play and substitute out. There are some sticky points with that in terms of those numbers are all to get to a transmitter compliance, and so there might be some carefulness there, but yeah, it's something that maybe I would call a little advanced usage or non-standard usage, but you can put in your own model and see how that might perform.
Now, are you gonna talk about? So obviously, this doesn't include crosstalk.
My next slide.
How that is allocated. Right.
Absolutely. So two very often questions that have come up. Let me postpone this update. Sorry. Two questions that have come up is, well, if I take this package model and I plot out the insertion loss, it's really high. Why is that? And that's because those capacitors representing the silicon die and the die attach, or the ball attach of the package, have a lot of loss in them. So it's about 1.3 dB for the 25 gig NRZ capacitors. The other question is, well, I have my own 30 millimeter package that I happen to design, and I compare the loss of that with what's in the IEEE model, and it's more or less or or what have you. And again, those are all parameters that are debated and agreed upon in the standard, and your particular implementation may have more narrow traces. It may have thinner conductors for density or something else. And so I guess, one of the takeaways is not to get too caught up in the physical 30 millimeters. It's more the overall electrical performance to tie together with the COM simulation. And then the crosstalk, as you mentioned, Scott, there's no crosstalk in these models. They are uncoupled differential pairs. And so how is crosstalk budgeted? Because obviously it's something that a real impediment to the system design, and it's lumped in two places. When you test a transmitter at a particular test point, I'll call it TP0 that I showed earlier. But if you were to test there's a parameter called transmitter signal to noise distortion ratio. That's a measurable point, and that's considered to be the place where you put the transmitter crosstalk. And then the receiver crosstalk from that package is actually part of the 3dB COM budget. Now, what amount and how it's allocated is not explicit, but that's in general where those pieces are intended to be.
Right, and so, and that's important because if you do have your own package and it has crosstalk and you use the TX SNDR as it exists, you're actually double counting the crosstalk noise. And so the best approach is to zero out crosstalk in your package modeling, at least at this point. Because right now vendors will not provide you the allocation for where that noise budget comes from. It's just a budget that everything goes into: silicon noise, on-chip silicon noise, bump out noise, and package noise. This is a good question. What is the maximum frequency the synthetic package model is accurate to? Will it cover third and fifth harmonics? And I guess I'd add to that, do we really need to cover third and fifth harmonics?
So well, it's a closed form solution, and I think the model itself works for high frequency accuracy, where at higher frequency maybe you get into different effects like modal effects, common mode. I could think of some things that maybe would fall apart for accuracy, but in general it's being used for 106 and 112 gigabit standards, and so that's what around, I think we want 50 to 70 gigahertz of data, and so I think there's a confidence there from the standard bodies. And then your question was third and fifth harmonic. There are filters that are applied 75% of the baud rate, and so you could say that higher in frequency could be devalued just from the filters that are present, that are band limiting in the silicon and other things.
All right. Thank you. Let's go ahead and go on. We have about 12 minutes.
Okay, I got two more slides for you. So here are some numbers around the 25 gigabit and the 50 gigabit PAM4. And I just want to point out, well, the transmission line parameters are the same between the two, which governs the loss and delay. But there's some nuance here in the amount of parasitic capacitance in the silicon die, as well as what the single value of the R die, resistance termination of the silicon. And you can see it's 55 here. It was 78.2 for the transmission line. I think the thought at the time was to mismatch those two impedances, and you see a 12 and a 30 millimeter length expectation, as well as this ball capacitance value. When you go to 50 gigabit, these numbers for the silicon die and the board attach get get better, less loss, less reflection. And then the characteristic impedance was pegged at 95, and the RDI went back to 50, stayed at 50. And again, all these parameters negotiated in the standard, and so I think less of them in terms of physical. I should design my package at 95 ohms rather than just a minimum capability that's required, or a reasonable degradation that goes in terms of parameters. The last slide here is to show where the 112, looks like I used 112 and 106, so sorry to be confusing there. 112 is an OIF data rate, 106 is the IEEE, but similar in the way that they're defined. So at what's happened, I've got 50 gigabit here in reference, but now instead of a single capacitor representing, there's a compensation circuit added here. And again, it's to get a little bit more accuracy out of these models, where a compensation circuit would perform a certain way, a certain filter function in the frequency domain. So you add this compensation circuit, the transmission line's there, but now the maybe the PTH through the core and the backside transmission line is represented by another transmission line, and then the ball attach value is much lower, but again, it's a play between these two elements. And so in general, it just gets more parameters to use for fitting, where someone brings into the IEEE here's my model package S parameter. Can you create a synthetic model that matches that, and can everybody agree on those numbers? The other thing to point out is that the transmission line loss is less at 106 or 112 compared to 50. So again, adding complexity to try to represent package models better is happened. And these links here, and I've got a collection of in the backup, the reference, are all public documents to go read more in depth.
Do you have a slide on the spreadsheet?
I did not include that. I thought it would be a little overwhelming, but yeah.
It's certainly included in all the other documents. We have a number of questions here. Okay, so going back to the long simulation you did, this was the simulation cascaded pieces of passive channels. I think the answer to that is yeah, it's a whole bunch of pieces that have been cascaded together. There's a person that's kind of interested in what you did there. So what I'd suggest is, Rajiv, that you send a message to Brandon, and I know that Brandon, you'll be happy to provide any other information that you have about that simulation run.
Absolutely.
So that gets rid of several questions. Oh, are the transmit and receive parameters updated every other year or less by COM or by the silicon vendors?
They are in the document. So, Ethernet 802.3 especially is a living document that's subject to maintenance. And I believe the latest full release was 2018. And of course, the drafts, the additional clauses that are released are released at, as the task force wrap up, I believe. But they're locked there. So maybe maybe I'll guess where the question was going is, maybe silicon gets better. Do they go back and update older generation parts? And I think the answer is no. That capability is set for that particular data rate. And the silicon provider may actually derate the performance to target that particular older data rate. Could be something that happens. So I think you're kind of locked into the values that happen when the standard wraps up.
And I'll point out something. Let's say that, for example, the standard used a DFE 12, a 12-tap DFE.
Mm-hmm.
If it turns out that your advanced silicon uses a 16-tap DFE and you're a captive system, that number can be changed in the spreadsheet so that a DFE 16 can be used. And so you'll, those simulations will see the advantage of the better silicon. Conversely, if the silicon doesn't perform up to the standard, let's say it's a DFE 5 instead of a 12, that also, we could still use the KR spec, for example, to simulate it, except that we change the number of DFE taps. And you'd see the degradation in performance due to that.
That's right. And I would say your mileage may vary in that I don't know if a lot of silicon vendors spend the time to create a COM spreadsheet that matches their capability. It's certainly possible. Maybe takes a little bit advanced knowledge of COM, and most of the answers I've seen to that question is, well, we agreed to the standard performance. I think the method that's usually used to bridge the gap between minimum and actual agreed to by maybe a specific would be to use an IBIS AMI type of analysis. I've seen that probably more often, but COM can definitely be tuned to a particular performance if a silicon vendor is willing to invest the time there.
Yeah, I think that's important. In fact, that was one of the questions about IBIS AMI, and that is, we can always, and one question that sort of answers everything, asks the major question: if you pass COM analysis, can your system still fail in BER measurements?
Well, if passing COM assumes that the transmitter and receiver pass compliance in all scenarios and the channel has all things considered. That's a very hard thing to have happen, I think. You know, if you think about all the things in manufacturing that could happen. So I'd say, you know, by the standard definition is guaranteed to work, there could still be issues that aren't accounted. I think one of the ones that power noise is one that's often cited is not being explicit in the COM simulation. So I think there could still be failures here, but I would say much higher confidence than maybe applying a frequency domain mask.
Yeah, what I would say is, and oftentimes it's generally failures occur due to the silicon just didn't work correctly. It's out of spec, number one. The power system has a problem and it's operating in some sort of a high noise or has some sort of power system resonance. And then the third place is, well, you just didn't model your interconnect correct. And that happens an awful lot. Maybe you don't have a good connector model. Maybe you didn't include all the crosstalk. Maybe you didn't include all the board effects. But if all of those things are modeled correctly and it passes COM, it just works. Mm-hmm. We see system after system after system that work well according to the COM spec. And COM allows us to know whether we're getting close to the threshold of failure pretty rapidly. Were there silicon RX and TX taps or knobs measured? When this was specified by the committee, I guess the question really is were all the different implementations of the silicon considered?
You know, I would say some, you know, again, the actual silicon implementation is considered the IP of the silicon vendor. I've actually seen channel providers, they don't want to share exact physicals of their channel, exact implementations either. But, you know, there's always a debate between maybe an FFE, receiver FFE based architecture versus a DFE is a popular one for optics type connections. I would say a lot is considered. I don't know if all methods are considered, and I see people cite papers. So it's this type of receiver and transmitter was in a paper, and we'll talk about that implementation. It's just a lot. What's usually implemented, receiver designers have a good idea of how to make performance similar to that, given their particular design.
Very good. The question here is how accurate is a COM simulation compared to I diagrams and S parameters? And I'll just answer that by saying it is based on the S parameters. So the S parameters are used for the base simulation that's done. And if you, it is a statistical simulation. But if you zero out all noise components, you're left with an S parameter simulation of a channel, and that matches. And that's been done. It was done in the characterization of COM very early on. Mm-hmm. That's correct, right?
That's right. Yeah, a lot of times COM, or initially, and even now, I ran it in COM. This is in the standard committee. I ran it in COM and also ran it in my MATLAB Simulink simulation and maybe my IVAS AMI, and they're within a certain amount, and that feels good. I mean, there's always, I think that's continually questioned, which is healthy, but the general consensus is COM is a pretty good tool for standard development.
So Rajiv here says you haven't mentioned ERL in addition to this, and yep. For good reason. That's an entirely another presentation that I believe we need to actually present. We don't have it on our work, but ERL can be used in conjunction with COM to help you characterize the devices that are within the interconnect channel.
That's right. If you download the publicly available MATLAB tool that runs COM, ERL comes out of those calculations. So it's very much in center stage since it was introduced, I guess at 50 gig PAM4.
Is JCOM related to COM?
Not familiar with JCOM.
JDAC, that's JDAC COM, and that's for DDR channels.
Oh.
Now going to statistical simulations.
I'm not familiar.
I'm not sure how that's diverged from standard IEEE COM, but I know it's using a lot of the core functions. But beyond, Rich Melich just chimed in. JDAC was derived from COM, but it's another tree and it's another standard body that's doing that. But it is the same kind of analysis because we found it valuable in SerDes channels. It's also valuable in DDR channels for high performance.
Hey Scott, hey Brandon.
Yep.
We have unfortunately we have reached our time limit on our presentation this week, and we appreciate as always the activity on the Q&A board. So we appreciate everyone's participation here as well. So we want to thank Brandon for such a great job on IEEE COM. Scott, thanks again for the as always lively discussion back and forth with all the question and answers. And again, we appreciate all our attendees listening in. Just a cleanup or two. Just a reminder to everybody, we are going to go to a 2-week cadence on our GeekSpeak webinar. So next week we will not have a presentation. Our next presentation will be in 2 weeks with Istvan Novak. So we'll look forward to hearing from him. As always, both the recording and the presentation will be available within probably not till early next week due to the due to the U.S. holiday observed tomorrow. But those files will be uploaded to samtech.com/geekspeak, where all of our recordings and all of our presentations are focused. If you have any technical questions related to SI, please feel free to contact our signal integrity experts, such as Brandon and Scott at sig@samtech.com. And if you have any questions specific to GeekSpeak, please feel free to email all of us at geekspeak@samtech.com. All the other questions we haven't answered, we'll post in a file in the follow-up email, and we'll look forward to talking with everybody again in 2 weeks. So thanks again, everybody.